This meeting is being recorded.
Now, in section 2 from chapter 12, we're going to explore the acidity of alcohols and phenols, and this term here, alkoxide, as well, which results when we deprotonate our alcohol. So, if you notice down here, we need a fairly strong base to deprotonate an alcohol, and commonly used is this sodium hydride, so NaH. So that's shown here after it ionizes in our solvent in solution. So we have sodium, and then we have this hydride ion here, so a negatively charged hydrogen. We see this proton transfer come, and it'll pluck this proton here, and then these electrons would then be deposited onto our ethanol. So now the deprotonated form of ethanol we see is an ethoxide, an alkoxide ion that results in our solution. And this would also cause a hydrogen gas to be released in this process as well. So we would see some bubbling in our test tube or what have you. So again, the deprotonated form of our alcohol results in this term, this alkoxide, this new compound that we're told about. So when we have the reagent used to deprotonate our alcohol, sodium hydride can be used, or sometimes metal can be used as well. So we just have sodium metal or lithium or potassium metal, and we see this deprotonation result as well. So we end up with the same alkoxide, and this also evolves some hydrogen gas. So let's take a look at how we can compare the acidity of our alcohols or phenols. So similar to what you might have seen in chapter 3, where we compared organic acids one to another. When we compare alcohols and phenols, we're going to compare the conjugate base, the alkoxide ion stability, just like we looked at deprotonated forms or the conjugate bases of other alcohols. I'm sorry, of other acids rather. So now we're going to look specifically at the alcohol conjugate base. So say we have a deprotonation occur on an acid or on some compound, and it results in a negative charge on a carbon. So any alkyl group here. This will be the least stable conjugate base as compared to the more electronegative nitrogen obtaining a negative charge. And then we have our alkoxide in this category here. So the RO, after being deprotonated, our alcohol would be ROH, right? So after we deprotonate our alcohol, we would end up with this right here. So this will be the focus of our comparison between different alcohols or phenols to compare their acidity. But down here, we can see in general, things like our alkanes fall in this category here. Then we have things like amines in this category, alcohols. And then these are those HCl, HBr, things like that, the halogen. So we'll list things like that in this category over here. Any X, any of the halogens that form acids would be in that class. Then these are the most acidic compounds we know. So HCl, HBr, HI. So let's see how we can rationalize using Ario, right? Remember, we can look at the atoms, electronegativity, when we compare same groups, or sorry, same periods across the periodic table, we look at electronegativity. And if we go down, the larger our atom, we can also compare size, right, to form more stable conjugate bases. If resonance is possible, inductive effects are I, and then orbital. So let's take a look at how resonance can help us, since we've already looked at the atom involved. If we were comparing if resonance is possible for our conjugate base, that's how we can determine if we have a more stable conjugate base, right? So we have cyclohexanol, say we deprotonated this. We have all these lone pairs now on our oxygen, but we do not have resonance possible with the alkoxide conjugate base that results for cyclohexanol after it's deprotonated. But if we were to deprotonate phenol, so this is gone, we see down here we have multiple resonance forms, some more stable than others. But the phenol here we see has a highly lower, or much lower rather, pKa value. So this is much more acidic due to the fact that it has resonance stabilization of its phenoxide ion that results after deprotonation. So resonance stabilization makes it about millions of times more acidic, and we can see there's like 8 powers of 10 between these two pKa values. So induction, that is another factor that can affect the acidity of compounds, specifically with alcohols here. Say we have ethanol over here, which we know has a pK around 16. If we were to add very high electron withdrawing groups like these halogens here, these highly electronegative atoms, these chlorines, this inductive effect would occur, and it would be that much easier to remove this proton because of all the electron withdrawing groups here, kind of pulling that electron density away from that OH bond. So that's why we see trichloroethanol is much more acidic than its parent acid, just ethanol. Another effect that, or another factor that can affect our acidity of alcohols is something called solvation. So whether or not there's some steric hindrance due to these bulky groups in tert-butanol here, we may have less access of a solvent to deprotonate our compound and actually destabilize our conjugate base as well. So tert-butanol would form a tert-butoxide alkoxide ion upon deprotonation, so that we can see here ethanol, this ethoxide after deprotonated form of ethanol, is much easier to be solvated because it doesn't have these bulky methyl side groups. So the solvent is able to stabilize that conjugate base better. So that's why we see that ethanol has a lower pKa value than butanol, and it is due to that solvation effect and the stabilization of the conjugate base for ethoxide. So we'll take a look at how to prepare alcohols from alkyl halides in our next video.